Okay, now let's talk a bit about the photoelectric effect. Photoelectric effect is something that Einstein discovered and actually won a Nobel Prize for his discovery. And the photoelectron effect is the property that, let's get to my right page here, the property that light has and metals have. Because if you take a metal, draw a metal, because metals have these extra electrons that they're pliable with, they're willing to give it away with, but they're still holding on to that electron with a certain amount of capacity. If we can shine, or what was discovered is, if you shine light, when you shine light on metals, the light has the ability to knock electrons out of the metal. And so if the light can hit it with enough energy, an electron will be emitted. Yes, sorry. So if light can hit it with enough energy, and one of these electrons can be emitted. Okay, so I'm just going to use, or I'll use the program just now to show you a little bit more, but there's something that we need to understand just before we go on, that light is a very mysterious something. Okay, one thing is because light acts as a wave, okay, which means it has certain properties that's like waves. Now we don't do waves anymore really, except for Doppler effect, to that extent, so that I can explain and you can understand certain properties like diffraction and things like that. But light acts as a wave in the sense that a wave has a wavelength. Okay, so a wavelength is the distance of a wave from its one peak to the next peak. That is the wavelength, and we use lambda. Okay, a wave is also something that moves. So a wave also has a velocity, and the velocity is measured in meters per second. So we literally see if this top, as time goes by, that top has moved. Okay. And after a few seconds, the crest is now a little bit further onwards. So in other words, there's displacement between this time period and that time period. And so displacement of that wave over the change in time will give me the velocity of that wave. Okay? So wave has a wavelength, that's how far the different crests are apart. It has velocity, that's how quickly that wave moves through space. And then, as a result, because it has velocity, okay, every second a certain number of waves pass a certain point, okay, and that is called frequency. So the frequency is, if I was standing at this point, this wave is moving. Every second I count how many crests are passing me. I'm counting the frequency, okay, and the frequency is measured in hertz. Okay, how many passes me at a point. Now, there's obviously a relationship between how many crests pass the point, and per second, and the velocity and the wavelength. The longer the wavelength, the fewer crests will pass every second, because if the wavelength is long, then it's going to take long before I get to the next crest. Does that make sense? And the quicker the wave moves, the more crests I can count. Okay? So in other words, your frequency is directly related to your velocity, but indirectly related to your wavelength. The longer the wavelength, the smaller the velocity. So this is meters per second, and this meters, is it meters per number of wave, or no, this is just in meters, so yeah, something like that. Let me just make sure. No, I'm right. Thought I'm right. Okay. Or I could just say velocity is frequency times the wavelength. I'm just multiplying both sides with the wavelength. But nevertheless, that's just the relationship between in waves. And for light, that's the case as well. The only thing about light is his velocity is constant in a vacuum. Okay. In other words, in a vacuum, light has a velocity of 3 times 10 to the power of 8, I think, meters per second. Okay, that's how quick it goes. So, but light can have different frequencies and different wavelengths. Now, that's the one aspect, and we're going to look a little bit more about what does different light with different frequencies look like, because actually what happens is when the frequency of light is different, the way it looks to our eyes is different. So for example, red light has got, I think, a lower frequency. Oh, I forgot, I can't remember now. We'll look at that. Compared to blue light and purple light and things like that. Okay, but we'll look at that just now. That's the one property of light. The other property of light is what we see in the photoelectric effect, is that if I'm able to knock something out of the way, it must mean that I have mass, because I'm making a collision. Do you understand? In other words, there's a property of light that it acts as a particle. A particle has the property that it has mass, and it follows the principle of momentum conservation, and that's what we see in the photoelectric effect, is the particle nature of light. It acts as a particle. Now usually waves and particles are distinct. They're not, we don't encounter them in the same way. Or in the same thing, but in light we do. We encounter light as waves and we encounter light as particles. Now we'll talk more about this, but before we can understand the particle nature of light, we need to first understand the wave nature of light. And for that I'll use the... Okay, I said 3 times 10. What is the exam say? Okay, let me just check here. 3 times. Okay, so they just rounded. Okay, the actual number is 2.8. They just rounded. Okay, if light travels through a different medium, like through air, through the atmosphere and through water and things like that, it does change, but we'll stick to the speed it has in a vacuum. And so what do I want to show you here? Okay, so what I want to show you here is, this is the light, the spectrum and the frequency that light waves can have. So notice here, it's the frequencies that light waves can have. So notice the relationship here is, we said that for light, okay, our velocity is a constant. So now we're going to use it as a constant. In other words, that is going to be a constant. So frequency is equal to a constant divided by a wavelength. So in other words, the longer my light wave, the shorter my the quicker my the longer the wave, the lower my frequency. The bigger my frequency, the smaller my wavelength. Okay, and that makes intuitive sense. If I have shorter waves, I'll count more of them every second if the speed stays the same. Okay, so just keep that in mind as we look at this table. So here you can see just a depiction of light frequency. Now here is the rainbow. That's the colors that we can see with our eyes. And the colors that we can see with our eyes has a wavelength in nanometers, okay, that means 10 to the power of 9, of between a little bit less than 400 and a little bit more than 700 nanometers. Very, very tiny wavelengths. Now, the smaller those wavelengths, in other words, the higher the frequency, you'll see the frequency increases to the left, the more blue it will be. Okay? On the other side, however, it will become more red. The longer the wavelength, it becomes red. Okay? Infrared is the colors that we get. The wavelengths of infrared is longer wavelengths, but our eyes can't see it anymore. We can't distinguish infrared. Certain animals can see infrared light. For example, an example of infrared light is a remote. Your TV's remote uses infrared light. So you'll see there in front is an LED. You can't see that LED even when you press so you can't see it blinking or anything like that unless there's another button on somewhere. Now the TV has an infrared camera that can detect infrared light. Okay, and how does it do it? I'll show you. That's now what the photoelectric effect is. Okay, so infrared light is longer, then microwaves is even longer. Now notice the wavelength gets longer. A microwave is a light, and it's really what your microwave uses to make food with. Okay, I think so. Okay. To make food with. FM radio is actually light waves. It's not, no, let me correct me. It's not really light waves. It's called electromagnetic waves. It's these photon particles, these little packets of energy that gets released. Okay, but if we go in the other direction, you'll see this is very high energy, high frequency light waves. For example, UV rays is the rays that from the sun that's harmful to us. Okay, X-rays are so strong is that they only bounce off the really thick material. So for example, that's why they use X-rays to take pictures of your bones, because they only bounce off. So for example, the reason why light bounces off the wall or off of my flesh, for example, is because the reason why I can see my flesh is because light is bouncing off of my flesh towards my eyes. X-rays won't bounce off my flesh. It will only bounce off thicker, more denser material. So it will bounce off my bones back. And so they've got special cameras that can then X-ray you, and then the cameras can pick up the light. But again, for our eyes, we can't see it. We can't distinguish X-rays. Okay, gamma rays is very, very dangerous. We find them very far out in the universe. Gamma rays. Okay, but just a little bit, a few interesting things about light. Okay, and that it acts as a particle. Now, energy. Obviously, because light are these packets of energy called photons. Light itself we can measure that energy using this formula. The energy that a certain light or a certain frequency of light has can be measured with this formula, HF, or can be given with that formula. Now, in other words, that is taking Planck's constant, which is given there, 6,626 times 10 to the power of -34. So let's use the one that's on the tab. I'm sure it's a simpler one. Why do I keep losing that one? Oh, there it is. Planck's constant here is 6.63. 6,63 times 10 to the power of -34. So this is a constant times the frequency of that light. So notice if I now go back here, that frequency is increasing in this direction. See, increasing frequency. So the more I go to the blue end, or actually the violet end of light, the more energy that light has. So a low energy is something like red light has low energy, okay, and the more energy it has, the more blue it becomes. You'll also see, for example, when a blowtorch doesn't have a yellow or a red light, okay. A blowtorch has a blue light. A blowtorch is a torch used to cut metal with. It has a blue light. The more blue the light is, the warmer it is. Okay. Sorry?
I guess that's quite harmful.
Harmful. Well, a blowtorch will cut you in half, but I'm talking about just the energy that you see that's released from a flame. The more blue or green, or like a red flame would be something that's glowing red. Yes, it's very hot, but it's not as hot as the yellow part of the flame. While sometimes you can see the blue part, that would be the hottest part of the flame, okay? So the more you go in this direction, and UV light, which we can't see, that's ultraviolet, violet being purple, ultra being extra purple. So ultraviolet light's energy is much more than the energy of these. And obviously the more we go, and that's why X-rays are so dangerous. When you go for X-rays, it's they always say wear protective gear, things like that. The people taking X-rays must wear special suits and things like that. I think you even put like a lead thing over your head and things like that. But that's because the energy is increasing in that direction. Okay, so that's one thing. But now we can change this formula slightly. So I'm not going to, obviously we're just going to use the H to replace. But we've said that frequency is directly related to the velocity, which for light is a constant c. And it's not light, it's for electromagnetic waves. So it's not just visible light that we can see, it's any electromagnetic waves, whether it's ultraviolet or the light that we can see, divided by the wavelength. So this is just another formula that will come into play. Now, the reason why this is important is obviously if I want to knock an electron off of metal, now why would I want to do that? Well, it is to my benefit to get electrons to move. It generates electricity, okay? So that's, for example, how these sun panels that charge electricity, that charge something that works with sun energy, is using the photoelectric effect. It's causing the sun to cause electrons to be knocked and move off of the metal or whatever they're contained in, and as a result we're causing a current.
So could you use solar geysers, for example?
Well, you get different types of solar geysers, but if the solar geyser works with electricity, then yes, then it's photoelectric effect that is being used there. Okay, so so this is the energy that a light wave will have. Now we need to just ask, well, with how much energy do I need to actually knock an electron off? Because it's no use I have energy, but I don't have enough energy to knock him off. And then they found that different metals require different amount of energy to knock the electron off. And it does make sense, because I mean different metals have a different desire to give away or to keep their electrons. Okay, so in the same sense, it's going to require more energy to get rid of that or to get it to move. Just like the standard electron potential, different metals reacting with one another has different capacity to attract them. Okay, so in that same way, and the amount of energy that you need to knock an electron off of a metal is constant for that metal. And that is called the work function. The work function. So the work function is the minimum energy needed. Minimum energy needed to, they say, to knock an electron from the atom. Let's call it the metal atom. Okay, so in metals they have extra electrons. The electrons are floating around in the metallic bonds, as you can remember, and they can get rid of these electrons, but you need to hit it with sufficient energy, and so by hitting it with sufficient energy you knock that electron off. Okay, so let's say I am hitting this with a certain light that has enough energy, or let's say the light that I'm hitting the metal with does not have enough energy to knock off electrons. Okay, then nothing's going to happen. Okay, the thing is just going to heat up because of the energy that the light has. It's going to excite the electrons, but it's not going to knock them off. Okay, but let's say now I do have enough energy to knock it off. In other words, the energy, and sorry, the work function is specific for every metal, has a unique minimum energy needed to knock electrons off. And for every element work function, it's a W0 at the bottom. That represents a unique value, and it will be a constant but for that metal. Now let's say now that the energy that I have is enough to knock it off. Then the energy that the light hits with minus the energy that it used to knock it off, the energy that is left, okay, is the maximum, and I should put a K there. The energy that is left is the energy, or all that energy went into the electron. So if I have light hitting with enough energy, more than enough energy, the extra energy that I had now goes into the electron, because the electron is now released, and the electron now has energy. What type of energy? Kinetic energy. Okay, so in other words, and so the difference between the energy, which now remember the energy of light is given by hc over the wavelength, minus, this is the energy needed to knock it off, then energy that is now left over is now the kinetic energy that the electron has. Now it's important to understand that is the maximum energy. It doesn't mean all the electrons that are leaving, that's being knocked off, has that energy. That's just the maximum energy it could have. And the reason why that's the maximum energy that it could have is because not all the electrons are on the surface. This is the minimum energy to release it. It could take more than that energy. So I could be subtracting more than just W0. So and if I'm subtracting more, it means my answer is less. So the absolute biggest value I can get is by taking the energy that the light hits with minus the minimum energy that's needed to knock it off. Okay, so do you understand why this is the max value? Okay? Okay, so let's say I just want enough energy to knock it off. I don't want him to have any extra energy. I just want to know how much energy do I need to at least just knock them off, even with no additional velocity afterwards. That would mean that I would need a minimum amount of energy. Not a minimum amount. What is the minimum amount of energy needed? Is obviously must be equal to the minimum the work function. Okay. Now this energy I get from taking the Planck's constant times frequency. This frequency is called the cut-off frequency. Just the frequency itself. Any light that has less frequency than that won't be able to knock off an electron. Okay, that's why it's called the cutoff frequency. If you've got less than this, you're not strong enough. So beat it. Okay. If you've got this or more, so in other words, the cutoff frequency. If I go to my, don't really. Here is a sketch with an example of the cutoff frequency. So here on the horizontal axis, they've put the frequency, and here is zinc. Zinc's the cutoff frequency to knock an electron off from zinc is at around here. What's that? That is 8, so that's 10, so it's about almost 10.5 maybe. 10.6. 10.4. I've given it there. About more or less 10.4 times 10 to the power of 14. That is the minimum frequency that you can have before you start knocking off electrons. Now, the higher the frequency is, and so notice on here, on the horizontal axis, I think this is called electron volts. That's the unit of energy that a moving electron has. We use electron volts. We'll look at that. But now you can see the higher the frequency, the higher the electron volts, or the higher the energy that electron has. But before this, if we follow the red, electrons have no motion outside the metal. Okay,
So
and
is the 10.4 the work function?
no, the work function is in joules, so it's energy. The 10.4 is the cut-off frequency. Now, you are correct in saying that because remember now, we have that this is true. The minimum energy that I need must equal the work function. But now the minimum energy that I need is h times the cutoff frequency is equal to the work function. So the work function is equal to h times the cutoff frequency. So if I just take this frequency that I have in this picture and I multiply that with Planck's constant, you will get the work function for zinc. Make sense? Okay, but this, because that frequency, work function is in joules, it's how much energy I need. This is just how much frequency I have, but to know, if I know how much frequency, I multiply with Planck's constant to get how much energy the light has. Okay, so what I do want to show you is this is the remember we looked at that earlier, a little bit less than 4. Do I have it here? No, I closed it. This is the frequency for light, visible light. And notice that visible light that I can see, does not have enough energy to knock an electron off of zinc. This is violet, so I'll need ultraviolet. I'll need ultraviolet light to be able to knock off an electron. Okay. Okay, so here we're just explaining that that electron volt. An electron volt is the unit that we use for the energy of an electron. So the energy of an electron, or let me rather say like this, you might remember that volts is the joules per coulomb. Okay, and a coulomb is in our table, one electron has this much charge. So if I wanted to talk about an electron volt, electron volt is the amount of energy that one electron will have. So this is the volts is the amount of energy that a coulomb of electrons will have. So an electron volt is just the amount of energy that one electron will have. So you'll see that it is simply taking the 1 times the the number of electrons in a coulomb. So if I know if I know what volts is, that's per coulomb. But there are 1 coulomb is 1,6 times 10 to the power of 19 electrons. Okay, did I do that correct? So I'm lying. One electron is that many coulombs. So an electron volt, electron volt, that would be taking the joule. If I want to solve joules as energy, okay, I will take voltage times coulomb, which is just then for one electron would be 1 volt times 1.6 times 10 to the power of negative 19 coulombs. So an electron volt is 1,6 times 10 to the power of negative 19 joules. Okay, so an electron volt. And the reason why we use this is because and that is a very small number. That is the energy that 1 electron volt will have, or that's the unit 1 electron volt is that many joules. It's a very small number because 10 to the power of negative 19 is very small. But that's true. An electron itself is so small that his kinetic energy will be so small because his mass is so small. And his kinetic energy is half mass times his velocity squared. Okay, so we work with small units, so it's no use that we use normal joules because it's just too small. Okay, so that's just regarding the units. Let's just quickly go back to just understanding what are we going to look at. We are going to look at light with a certain energy hitting a metal surface. And the metal surface has a certain work function. The extra energy is the max energy that an electron can have if he's being ejected by this metal surface. In other words, it is the difference between the energy that was put in minus the energy that was needed. It's almost like paying bail. Okay. Paying bail is a certain amount of money needed to bail you out of here. Whatever extra money I have left, you can have. Almost think of it like that. But now, kinetic energy, remember, is a half mass times velocity squared. Okay, is equal to this energy that I worked out. Now, this is the energy of the light, which was just, what was it? CH over lambda. Was it like that? Okay, minus WC. So I just want to show you the big picture here. These are all then values that I can use to find certain values. That's a constant, that's a constant, and for each question this will be constant because they will tell me what lights am I using. They will tell me what surface am I using, so that's a constant. And as a result, the mass of an electron, because this is kinetic energy for an electron, the mass of an electron is constant. It's given here. Okay, mass of an electron is the mass of an electron. It's constant. So that's constant. So I can use this to work out at what velocity is he leaving the metal. Now, if I increase the velocity at which he is leaving. So now imagine he is leaving. It means there's a few things I can measure. I can measure current. Current is what? The number of electrons that pass a certain point every second. Doesn't matter how fast one of the electrons go. Okay, that's not going to affect the current because it's just one electron. What does affect the current is the number of electrons that is being ejected every second. Okay, so in other words, increasing the current increasing the light, the energy of the light. So in other words, increasing the frequency or decreasing the wavelength of light won't increase the current. What it will, however, do is it will increase the energy of every electron coming out. And what will that increase? That will increase the voltage, because voltage is the energy per coulomb. In our case, we're using electron volts, which is the energy per electron. Does that make sense? So increasing the light does not increase the current that's being generated, but it increases the voltage, the energy that I can work with. Now, if you increase voltage, current is equal to voltage over resistance. So if you increase voltage, you are increasing the current. Okay, if your resistance, that is. But what I meant earlier when I said it doesn't increase the current is the effect of increasing energy affects voltage. Voltage in return affects the current. Okay, so it does affect the current, but it's through voltage. The other thing I can do is increase the intensity of light. Now, what do we mean by the intensity of light? Well, here's a good example. So, for example, if I take a torch and I shine the torch on a certain surface. Have you ever used a magnifying glass to intensify the light? Okay, so what do we mean by intensity? Intensity didn't increase the wavelength, it didn't increase the energy. All it did was it increased the number of photons that hit a certain area per second. So, for example, it's like if, let's say, did it rain where you guys stayed yesterday? Did it rain? Okay, so let's say all the rain, you stayed in Midrand, you stay here in town, I stay there by Midrand, okay, by mainland. If we take just that area, but we take the same amount of water that fell, and we only let that fall in my house, do you understand? Yes. The intensity has increased. It's the same amount of energy, the same amount of, but it's now covering a smaller surface. Now, what that would do so increasing the intensity of light just means I'm increasing the amount of photons. Remember, these are now little packets of energy being bombarded to the surface. Now, increasing the intensity doesn't increase the velocity with which you're increasing it. It doesn't increase the energy that they themselves have. That was what will happen if you increase the velocity. It simply it doesn't even decrease the space they fall in. It just increases the number that hits every second. Now, what will that affect? If I have more photons hitting the surface every second, what will the intensity? Will my electrons leave with more energy?
No. Be more
electrons leaving. Yes, more electrons per second will leave. So what will that affect? Voltage or current? Current. Current is the number of electrons that's leaving every second. So increasing the intensity doesn't increase the energy that you can deliver, but it does increase the number of electrons that can deliver energy. Does that make sense? Great. Then we get this. Then that's really it. So what is meant by threshold frequency? Yeah, that's the same. That's the minimum frequency needed to knock an electron off, from the surface. Okay, so let's go and look at some questions in the exam. So we had one here. This was actually quite a difficult question, I think, in this exam. So here they say the photoelectric effect has many practical applications. A photocell, such as the one below, is used in burglar alarms such as this one. So an ultraviolet beam, you can see there, they're sending out an ultraviolet beam of wavelength. So they give you the wavelength of ultraviolet. Now again, we need at least ultraviolet to use the photoelectric effect. So an ultraviolet beam is coming in here. It's hitting the cathode. Okay, so notice that the cathode in this case is then releasing electrons. In this case, it's releasing electrons, and electrons are then thrown, are being ejected by the cathode. These are the electrons coming, and they collected by the anode. You see, and then they, in the anode, then are moving towards the positive end, are now attracting them. So the anode again is the one that in the external circuit electrons are flowing away from. So you can see in here. Now this is what happens when a person interrupts the ultraviolet beam. So how the how these burglar alarms work, you've seen they have a little thing like this, and then they have a thing that shines ultraviolet light, and this is kind of a camera. That's where the photocell is. So the ultraviolet light shines, but then off of every object it is returned. Now under normal circumstances, when you switch it on, it then this happens, and this burglar alarm now locks in what is the current in this situation. But now someone comes and they interrupts that beam. They walk past the beam that is being reflected back, and so what happens? There are now an interruption, so there's not electrons flowing, or there's fewer electrons flowing because you've interrupted one of the beams. There's fewer electrons, so the current is reduced. And so when a person interrupts the ultraviolet, there's a sudden drop in current, and it activates a switch which sets off the alarm. Okay. Define the term threshold frequency. So that's the minimum amount of frequency needed to eject an electron from a certain material, metal. How will an increase in the intensity of the ultraviolet light influence the ammeter reading? It will increase the ammeter reading. Explain your answer. Well, an increase in the intensity increases the number of photons hitting the metal surface per unit area, increasing the number of electrons being emitted every second, which increases the current. How will a decrease in the wavelength of the ultraviolet influence the ammeter? So if I have a wavelength, what happens when I decrease the wavelength? Am I increasing or decreasing the energy?
It stays the same.
Let's look at our formula. Okay, so in this case, my question is, am I increasing the energy that the electron is leaving with? Is it the same, or am I decreasing with? CH. If wavelength forms part of the equation, then it can definitely not stay the same.
So it will, if we increase the wavelength,
Decrease the wavelength.
okay. If we decrease the wavelength, we will increase the energy.
Good. Because if I decrease this, I will increase this. And this has a positive in front. So if I increase this, it will increase that. Make sense? If I increase the work function, obviously it's got a negative effect, so it will have a negative effect on the energy. Is that okay? Okay, so it will increase. A decrease in wavelength. The work function of three metals are shown below. Okay, so the work function, this is the amount of energy that I need to eject Give a reason why different metals have different work functions. Well, different metals require a different amount of energy to knock their electrons out. Okay, the cathode of the photocell, okay, in the burglar alarm is made of an unknown metal. The average speed of the emitted electrons is, now they give the average speed. Now, the reason why we use average speed, of course, is because and I didn't explain that. Maybe I must quickly see if I can explain that. Okay. Notice again that we can only work out the maximum velocity. Okay, we can't find the average velocity. So just so that you understand why in this question, you'll see when we try and do this question, we get to an answer that doesn't really fit any one of these. Okay, and then we'll have to choose why doesn't it fit these ones, or which one does it fit best. No, I'll explain. No, man, you'll see now. The average speed of the emitted electron is that much. Identify the metal by performing the relevant calculation. Okay, so if I find that my maximum speed is close to, well, let's do them. Let's do it. Okay, so they give me the velocity of the electron. So if I know what the average speed of the electrons is, I can at least work out what the minimum energy is that those electrons have when they're ejected. Okay, not the minimum, but an average energy is that they ejecting with. So in other words, if, let's work with it here. Where is it? Average is 4.78 times 10 to the power of 5. So the energy, the average energy that they are ejected with is a half mass. The mass, I'll get it now. I'll put it in now, times 4.78 10 to the power of 5. 4.78 times 10 to the power of 5 squared. Remember, half mass times velocity squared. And then let's just get the mass of an electron on our formula sheet. Go past it, there we go. 9, 11, 10 to the power of 31. 9,11 times 10 to the power of negative 31. Okay, so that, if I calculate it, that gives me 9.11 times 4.78 divided by 2, okay, is equal to 21.7729. 21,7729. And now I just take these two times 10 to the power of negative 31, 10 to the power of 5 gives me 10 to the power of negative 26. Okay, please don't round off. I'm marking your paper 2s, and people are rounding off before their final answer, and if you round off 0,0041 to 2 decimal places, you get 0,00. You understand? You can't round off until in your final answer. And even if you do round off, don't just round off to 2 decimal places. Round off to at least 2 significant figures. What that means is 0,004132. Okay, round off to at least 2 significant figures. Significant figures means in front of them there's no zeros.
Because the thing is, like at the beginning of the exam, they tell us to round off to 2 decimal places.
Yes, but these type of, no, I understand that, but that's in your answer. Do you understand? That's your final answer. You'll see that's what they say. Your final answer, you can round off to 2 decimal places. Round off your final numerical answer to 2 decimal places. But even if your answer did come to something ridiculous, as small as this, rather than write it in scientific notation, 4,13. Now I've rounded 2 decimal places, times 10 to the power of 123. -3. Okay. So, but anyway. Oh, sorry, I made a mistake. This is 9.11 times 4.78 squared. Divided by 2 is 104. 0.74462, 104, 0.74462 times, and now it's not 10 to the power of 26, I do apologize. It's, and this is actually good I made this mistake, because people, the one person that actually did this correctly, this is where they made their mistake. They didn't square the velocity. Okay, and so when this is squared, that's 10 to the power of 5 times 5, not 5 times 5, 5 times 2. So that's 10. So this is 10 to the power of -21. Okay, so because this becomes 10 to the power of 10. Okay. Okay, that's the average energy that the electron has. Now, this is kind of the net, that's the extra energy he had after we took away the energy that the work function energy. Now the work function energy is what I'm trying to solve. So how much energy did we use to knock him off? So that is the energy we used to knock him off is the speed of light times Planck's constant divided by the wavelength, and they gave us in here the ultraviolet light that's being used has a wavelength of 2.3 times 10 to the power of -7, and so this is 3 times 10 to the power of 8 times Planck's constant, which is 663 10 to the power of -34. 663 times 10 to the power of -34 divided by the wavelength, I forgot now, (2,3 times 10 to the power of -7. 2,3 times 10 to the power of -7. So in other words, if I do this one, I'm going to take 3 times 6.63 divided by 2.3, and I get 8. I must just store it in my memory function, memory store, and so I'm going to take roughly 8, where is it? 8,69 times 10 to the power of, and now this is 8 minus 34 gives me -26, minus -7 gives me +7, so -26 plus 7 gives me -19. So this is the amount of energy that I hit it with. This is the amount of energy that was left afterwards. So if I move the comma 2 more spaces, you'll see it's 1,0407 times 10 to the power of -19. So the difference between these two, this is how much I gave it, this is how much it ended up with. The difference between these two is then the amount of energy that was used up in the knocking off process. Does that make sense? So in other words, the work function is roughly equal to 8,69. This, and again, this is the maximum energy that I could have subtracted. No, sorry, the average energy that I could have subtracted. The average energy. So 8,69 times 10 to the power of negative 19 minus 1,04. Okay, let's just do 2 there, that's fine. Because the reason why I'm doing that is because in here they only went to 2 decimal places. Minus 1,4 times 10 to the power of negative 19 is equal to 7,65 times 10 to the power of negative 19. Joules. Okay, now just keep in mind, is the average more or less than the maximum?
Less.
It's less than the maximum. So if I were to subtract the maximum energy from here, would my answer be more or less than this answer?
Emax is less, right?
No, Emax is more than the average. I am subtracting the average. So in other words, you can almost look at it like this, okay? That my work function is my energy from the light minus my maximum energy from the let's do it like this. No, my work function is equal to the energy from the light minus the maximum energy from that my electrons have. Okay, but now I know that Emax is greater than E average. Do you agree with me?
Yes.
Okay, but I'm using negative Emax, so if I multiply both sides with a negative, then Emax is smaller than E average if I multiply both sides with a negative. You with me? And so now I just add an E to both sides, so Emax, E minus Emax is smaller than E minus E average. And so this is my work function. My work function must be smaller than the answer I actually got. So if I go and look, the answer that I got is more, but can you see it's not equal to silver, but I don't expect it to be equal to silver because we used the average. So even though I didn't get the answer for silver, I do expect an answer. It could be any one of those, because I just know what the average one could be, and not necessarily what the average. So I basically know what the average average energy is that is needed to knock them off, while this is the minimum energy needed to knock them off. So I have the average energy that's needed to knock them off, but I still think silver is the best candidate. it makes sense. It's reasonable to take silver because it is less. Now, but let's say I had 7, my answer was something like 7,54. Now if you look, whoa, it's closest to silver, but according to what I showed you here, the work function must be less than the answer I get. So even though silver is closer, my work function must be less, because I'm working out the average. What I have, because I'm using average velocity, I've worked out the average energy that that is used to knock the elements off, while this table gives me the minimum energy required to knock them off. So my average energy can't be less than the minimum energy. So it would then go to zinc, which is the next closest one. Okay. But I really don't think it was a difficult question. I mean, it is worth quite a lot of marks, 6 marks, and even if you didn't get the right answer, you didn't know how to interpret that, you would still get 5 out of the 6 marks.
You see, that was my problem. I ignored the problem thing at your speed. So I got the answer as silver, but I didn't.
No, but you didn't do this.
I did.
Is that what you did?
Yes.
All these, but then you...
I didn't use the formulas you used. I worked with like some other funky way.
No, but you could have guessed silver. That doesn't make you... that you get 0 if you guess silver. You don't get a mark for guessing the right answer. You get a mark for showing that the right answer is silver. So what you could have done is you could have used this formula that the energy max, but that's fine. You should have still gotten full marks even if you didn't see average. But so energy max is C times H over lambda minus W0. That's here. That's that one, just with E replaced with K max replaced with that, well, I suppose it's this one. EK max is replaced with that, and energy is replaced with this. So you could have just used all of that. I just broke it up into pieces, and if I know the velocity, I can work out the energy that it has. If I know how much energy it has and I know how much energy I put in, I can see how much energy was used up by knocking it off. So it's, I don't know, for me it's reasonable. Oh, negative cookie you. What conclusion about the nature of light is drawn from the photoelectric effect? And that's the conclusion, the particle nature of light. The fact that light acts as if it has momentum, that it can give to other people its energy. So in the photoelectric effect we discover the particle nature of light.